xLSTM is a improvement upon LSTMs. We all know we all love LSTMs, but they've basically been replaced by transformers because transformers are just so much more expressive than LSTMs. So this paper is actually written by one of the original authors of the LSTM. I'm pretty sure they are one of the original authors of the LSTM. So yeah, they're coming back with another LSTM. Um, so like to begin, what's the problem with transformers? So like we all love transformers, we all love using them. However, there is a massive problem to them. So you basically have a sequence X, which is going to be of shape, say, S by D. So you have this matrix here, and this matrix is, say, like an S by D matrix. I'm flipping it. I usually just like writing it this way. But yeah, S by D matrix, and S is the sequence size, and D is the dimensionality of each vector. So what is this? 1, 2, 3, 4, 5. This may be I like cats, blah, blah, blah. So 5 words. I'm not that creative, but yeah, 5 words in each of dimensionality D. So D may be something like 1024 or maybe 16 something, 16,000 with the new transformers these days. Now, the problem comes whenever you project this to QK and V. So you project this 3 times to QK and V, and your attention formula is basically the softmax of QK transpose times V without the scalar reduction. But yeah, this is essentially what you have. And this right here is an inner product. And this inner product is a matrix of size S by S. So S by S matrix. And this S by S matrix is a problem because it gives you this quadratic complexity that you have to compute. So this matrix here is quadratic because it's, well, S by S, so the size is quadratic, and the time to actually do this computation is quadratic. And the problem is you can't actually like reduce this operation because you have this softmax here. So the softmax forces you to do the QK transpose. You can get around it with flash attention and stuff, but the basic problem is that this is quadratic. During inference, this is linear if you do key value caching. So basically, during training, this is quadratic, and during inference, this is linear in complexity. So 2 problems. This becomes intractable to train, and while you're doing inference, you can't do infinite inference because it becomes intractable to hold all your keys and values. And that's because if you look at the formulation, only the query changes along the rows. But yeah, anyways, if you go to an LSTM, it basically reduces the complexity by 1 order for both training and inference. So for a transformer, you have, say we have train and we have inference. You basically have S squared and S. But if you have a R and N, you have S and constant. So maybe I'll just write 1. And that's because you basically have this hidden state. So for an RNN or for an LSTM, generally you basically have this linear complexity whenever you're training, and that's because you have these tokens. So you have 1 token. This will end up going in the hidden state, and it'll give you your output token. And then we go to, HT, HT plus 1, and you send the next token through, and this will give you your output token. And you keep on doing this. And the linear complexity basically comes from like the gradients and the fact that you have to store, like every token you add, it doesn't increase it by every past token. It only increases the memory complexity by that 1 token. While in the transformer case, every token you add increases the memory requirement by every other token because of the S squared matrix. And then during inference, you basically have your hidden state here, HT. And every time you generate a new token, you just throw your new token in there. You get out a new prediction, and this gives you a HT plus 1. and you basically just scrap all this memory, so your memory doesn't increase, and then you throw another token in here, and you get your new hidden state, ht plus 2, and you scrap all this memory over here. So your memory increases, your memory doesn't increase at all during inference. So RNNs are quite nice in this sense, but they're a lot less expressive. Well, usually they're a lot less expressive than transformers. So the idea here is, how can we make an LSTM more expressive? And like LSTMs used to be the state of the art. How can we make this thing as expressive as possible? And they show that they can get near transformer accuracy with a lot less compute. So let's look at how they do that. So basically, the initial LSTM formulation looks like this. So this looks complicated. It's not that bad. You basically have a whole bunch of gates. So every time we have a gate, so you can think of a gate as basically taking information from the past or taking current information and saying, what information do I want to keep? What information do I want to send on? Or what information do I want to observe from the hidden state? So you usually see this diagram all over the place. I drew it out over here. Sigma is your sigmoid function, and you can think of the sigmoid function as a gate. If you have a value of 0, that means that you're allowing no information to flow through, and if you have a value of 1, that means you're allowing all the information to flow through. So it's a gate, and if you have if you have a vector as your hidden state, and you have another vector as your gate, if this is like a 1, it's saying all the information for this first part of the vector is flowing through. And if this part's, say, a 0, it's saying no information from here can flow through. So it's basically deleting all the information or saving all the information. That's how you can think of this. So I guess we could start over here. So the input here, basically, it doesn't directly go into the hidden state. So C is the hidden state you usually think of. It's like, this is the thing that's accumulating our information, and H of T, which is what you may expect to be the hidden state, is like the information that's being sent to the next state. So this is our accumulation state, and this is our hidden state, the information being sent to the next state. Or rather, the information being sent to the next state that like the model directly uses as, that the model directly uses. Because you basically want to use this to, you use this to use this for your gates. So if we look at the input, which is xt here, xt goes through these 4 different gates: zt, it, ft, and ot. And one thing to note is that these are all scalars here. So bear in mind, these are scalars, or they're not vectors. They generalize to vectors, but in this case, they're scalars. So our hidden state is a scalar, and this is an inner product between 2 vectors. So vector dot vector is a scalar. So you have a scalar here, you're adding it to another scalar, and you're adding it to a bias scalar. So every one of these gates is a scalar here. So the first gate, every one of these operations is a scalar, and then we send them through the gating operations. So I of t is our input gate, f of t is our forget gate, O of t is our output gate, and zt is basically squishing the input. So our input is our input isn't just xt, by the way, it's xt and ht. So these are our gates. This is basically the input. So what do we do with these? We have these 2 hidden states that we're going to be carrying around. This first hidden state is composed of 2 things. It's composed of this first thing here, which is saying, I have all this past information from every hidden state. Now, what information do I want to keep, and what information do I want to delete? So f of t controls that. And remember, f of t is the sigmoid of the input and the hidden state. So f of t is basically deleting or keeping old information. And then we say, we have this new information, and what part of this new information do we want to keep, and what do we want to add to the hidden state, and what part do we not want to add? So that's what this gate does. This gate's deleting, or keeping new information. This gate's deleting or keeping old information. This one is adding or not adding new information. One important thing to note is that if you do not have these, then your hidden state can grow up forever. So imagine I have a vector at time t. That's going to be an accumulation of t vectors. And if you don't have any normalization, such as this here, because this is essentially keeping the magnitude the same. The magnitude isn't going to increase. It's not going to increase very much. It's keeping it pretty steady. But if you imagine if you don't have these squashing factors here, keeping values between 0 and 1, then these values are going to blow up. They're going to blow up because this hidden state here will be unnormalized, and you basically keep on adding information to it, and it's going to blow up and it's going to diverge. You're going to run into problems. So you need normalization factors like these to keep your RNN stable. Now your actual hidden state here is the thing you're going to be using to get your output. This here is sent through right here, a squashing factor. So it squashes it. We use tan H. This keeps the values between -1 and 1. So it's, again, a normalization factor. And it's on the context, or it's on this hidden state here. And then we send this, we multiply it by O of t, which is another gating function. So this basically says what information do I want to keep and what information do I want to get rid of. And then this goes into the output. So this is our output. Now, if we go back to the drawing here, this may be easier to look at. So we have our hidden state here, which is our accumulation of everything. And this is our other hidden state here, basically the output hidden state. So we have these two hidden states. This is the accumulation one, and this is the one we send to the output. So remember that this one is used along with xt to give us our gating features. So the first gate is f of t, or f sub t. And this gate here basically says, what information do I want to forget and what information do I want to keep from the hidden state? So that's just this part here. The next part here is saying, what new information do I want to add? So it right here is our gate, and zt here is our squashed input. So we squash the input, we then gate that, and we add it to our context here. So that is this part here, right here. So this is the squash, and this is the gate right here. And then the final part is the output. So this part here is sent to the next part, or to the next token, but it's also sent down here, which is sent through the squashing tan H function, and then it's sent through the output gate. So that is this part here. So it's first squashed, and then it's sent through a gate. And then you get this output hidden state here, which is also used as the output. So if you stack these cells, this would be used as the input into the next cell, or rather the hidden state for that next cell above it. So this is a normal LSTM. Now, like I said, like LSTMs are cool and all, but they have a lot of problems, and they have a couple problems that they want to fix. So they want to fix, one, the inability to revise storage decisions, and they say they fix that by sLSTM, which is a little weird to me, but they mention that it does fix that. And then they also mention that, so they mention it, they fix it with the exponential gating, and limited storage capacities, i.e. information must be compressed into a scalar cell state, because remember that these are inner products, so these are all scalars here, not vectors. They say that they fix that by making it vectors rather than scalars. They also say that they do some stuff like rare token prediction, and they also mention that there's a lack of parallelism. So there's a lack of parallelism due to the memory mixing, i.e. the hidden connections between hidden states from one time step to the next, which enforces sequential processing. And they mentioned that you can do parallelism if you don't have memory mixing. So if you remove this memory mixing, constraint, which happens whenever you go to vectors, then you don't have this problem. And they remove this constraint by basically creating multiple heads that don't mix with each other. So these are the problems they want to fix. They want to fix the lack of being able to revise a storage, limited storage, and this memory mixing problem. So they first fix this by creating an sLSTM. So sLSTM takes LSTM and it only adds a few things. I underlined it in red, and it's these minor changes, but the minor changes can lead to big problems. Remember how I said that these here are normalized, like this hidden state here is normalized because this can only be between 0 and 1, and this can only be between -1 and 1. So this hidden state stays stable because the values only stay between like -1 and 1, or they stay around that. They don't explode or drastically decrease to -infinity. They stay in a nice stable state. They changed this to an exponential, which is not stable at all. So we have I and t and f of t, are input and forget gates, which were sigmoids, but they're now exponential functions. And this is to allow drastic additions or drastic removals. So in an exponential, you basically have like your curve here that goes to 0, which is between 0 and infinity. So instead of it being between 0 and 1, you have between 0 and infinity, and that allows you to drastically keep information and store it at a massive value like infinity, or drastically delete information and make it go to 0. So rather than values just being between 0 and 1, so you keeping the value or you removing the value, you can either remove a value or you can keep it and exponentially keep it. So keep it at a really high value. This basically models some importance, saying like if something has a value of like 10, like a gating value of 10, you're like, this is a really important value. While if something has like a gating value of say 1, you're like, I mean, this isn't that important. And if it has a gating factor of 0, you're like, yeah, I want to remove this garbage. That we need to remove this stuff so we can add more stuff in this hidden state. So that's the idea behind exponentials, but like I said, they're not stable. So to fix this, you add this normalization value here. So this normalization value here is similar to CT, except it's just an accumulation of IT and FT. And I'll show in a sec that this actually is stable. So, and these are not vectors, these are scalars, but I'm going to fix that. Scalars. And instead of HT being squashed by tan H, so over here it was squashed by tan H, you actually have this hidden state here be normalized, so just divided by NT. So yeah, we have our input here, so the input's similar, and we basically just have this other hidden state, NT. So if we look at the ranges of these values, NT and CT can basically be between 0 and infinity. There's nothing keeping them from being any different than that. They can actually be between -infinity and infinity if these values are negative. So they can range from, they can be any value. Now, what we want is we want a stable hidden state for the output. So like assuming we can store these -infinity values, which is may not be a good assumption, but assuming we can do that, we just need a nice output state, which is sent to the next state. So we want a nice output. And the nice output comes from this normalization here. And if we look at the normalization, it does actually lead to a value between 0 and 1. Like if you look at this, you can kind of expect it to be like that. You look, oh, if I divide C of t by NT, yeah, sure, that kind of looks like it would be between 0 and 1. If you write it out, it does actually go between 0 and 1. So we have C of t at NT and NT. And I don't write out a mathematical proof or anything, just like some intuition behind it. And you can rewrite this as just using the equations over there. You have ft ct minus 1 plus it zt divided by ft nt minus 1 plus it. So if we look at h0, h0 is just z0, which is normalized. Z0 is over here, which is just this inner product here plus bias. You don't have that. So that's stable between 0, 1, or stable, depending on how you normalize it. Then if you go to H1, you can write this out as F1 I0 Z0 plus I1 Z1 over F1 I0 plus I1. So if we basically assume that Z0 and Z1 are the same, just for the sake of argument, then you can extract Z and you get out Z, which is stable again. So this is just looking at the magnitude rather than looking at the exact values. So if you extract the magnitude, then it's fine. So the magnitude stays stable across states rather than exploding from negative infinity to infinity because you have this normalization hidden state here. So that's the idea behind the normalization, and they have a better proof in the end. I just thought this was more intuitive. So if we look at this, I drew out the additions in red. So this forget gate, this is NT right here. So NT. The forget gate also adds to the NT and NT because you need to you want this value for normalization. So it's a multiplication of NT and FT. I wrote it as an addition. It's actually a multiplication. Multiplication. So this should have been a multiplication here, but anyway, here is just an addition. So you take IT and you just add it here. And the third part is instead of this norm here being a tan H, so up here, it was a tan H. It's actually just a norm. So you take your current context here, and you divide by your other hidden state here, your normalization, and this gives you your output hidden state, which you can then use. You can then pass on to your next cell or the cell above it if you stack layers. And like I said, CT minus 1 and NT minus 1 can basically take on any value because it's exponential, while HT is stable, and that means that the output is going to be stable as well. So like I said, we've been working with scalars and all that, and you're probably like, why don't we work with vectors? I was thinking the same. The reason they don't mention that they don't really work with vectors here and they just work with scalars is because they have this thing called memory mixing, and memory mixing basically is this idea. I'll draw it out over here. So if we have it's this idea of like, oh, I have multiple heads, or I have this way of mixing between LSTM cells. So let's say I have like multiple heads. So if I have multiple heads, I'll take my input vector xt and split it into two vectors. I'm just going to draw it out as two vectors, but this is like xt1 and xt2 or xt2. So it's like two vectors at xt. So if we send this through an LSTM, let's just send x1 through an LSTM. You basically do an inner product and you get out some hidden state. So you'll have a hidden state that's a scalar. Let's just call this ht. Now, if I do this with another vector, I will draw it, say, I'll draw it next to it, xt2. This will give you another, we'll call this h1 and h2. So this will give you a hidden state at time t, but only for this here. Only for so these are independent hidden states. They don't mix with each other. Now the output vectors, or rather the output scalars, are also independent. So you'll get some output here, OT, 2, 1, and these are independent of each other. Now, if we look at this formulation here, the RT here, or the RZ here, is a scalar. So what you do is in the next, I'll draw it like this. So in the next step, xt2. What you basically do is you say, oh, this next hidden state here, xt2, is going to be composed of the previous hidden state and this vector here. It doesn't really look like a vector, but there. So the next hidden state is composed of the previous hidden state and the current the current vector. Same with this one here. Xt, whoa, t plus 1, 2, x1, t plus 1, ht plus 1, h1, and h2t plus 1. I'm getting my notation mixed up. There, like so. Now, what they say is if you convert this to a matrix, your h of t, like let's say we have our ht here, ht1 and 2, you can basically stack these together. And instead of your next ht just being a multiplication with a scalar, you can make it a feed-forward network. So that this next one, so that ht plus 1 will be composed of both hidden states here. And this hidden state here, ht plus 1, 2, so this one here, will be composed of not just the current not just the hidden state for this input, but also for this input over here. So ht1. So if you can kind of see that, basically proceeding to the next hidden state mixes information rather than it being independent from each other. So if you have multiple heads or multiple LSTMs in parallel, this mixes information. And they mentioned that that's a problem because you can't have these parallel LSTMs running. You have to mix information after every layer if you want to convert these to vectors, because if you convert RZ to a vector, or RI, or RF, or RO, it basically takes all the hidden states from every part of the vector and mixes them together, instead of having these heads that are parallel and independent. So the next part basically converts this to a vector operation and makes it where they can go in parallel. Like you can make this go in parallel, but these would all have to be scalars. So as soon as you make this into vector operations, then the hidden states mix and you can't have parallel unique heads unless you just make this a scalar. But more expressive power runs into problems. So they say they want to fix this by creating this mLSTM here. And mLSTM stands for matrix LSTM. So they say they convert this from a scalar to a matrix d by d. So instead of it just being this one scalar, we're going to have a matrix. And they do that by doing this simple operation where instead of the input being over here, zt, which is just a scalar, the input is now going to be an outer product between two vectors. So before we basically had a weight vector and our input vector, and we multiplied them together and got a scalar. Now what we're going to do is we're going to have a weight vector. We're going to have a weight vector, we're going to have our input, and then we're going to have another weight vector, and we're going to have our input. And this will give us a matrix because we do an outer product between the two. So that's basically the difference. And they formulate this in the basically with queries, keys, and values, so relating it to attention. And you get this formulation here. So the idea is you can store the queries and values. This is basically, like I mentioned before, in attention, whenever you're doing inference, you have this key value cache. This is basically what that is. This is basically your key value cache, except this is how you're actually training the thing. You're not doing it for inference, you're training the thing on this key value cache. So the first thing you do is you take your input and you project it to your queries, keys, and values. So now you have three vectors. So you have three inputs. Now the first input, or you then do this outer product, so vector product, and you get this this dV by dk matrix here, and this gives you your input. So your C matrix, or your C hidden state is not going to be a scalar hidden state. It's going to be a matrix hidden state, which is of dimension dv by dk, because you're doing this outer product here. The input here is just a scalar for some reason, but it's still a scalar. I think that's just so they don't have memory mix, but it's a scalar, basically just for this whole hidden state. So scalar, how important is this current token? How important is this time step? And they also use this exponential weighing. So they basically take all of sLSTM and they're converting it to this matrix operation. Now, this also means you have to normalize by k, so here, and that's another addition they have. So instead of you just normalizing by f and I, you also need k here because we're doing this matrix operation here. And if you write it out, it also becomes stable again. So these are the two additions you're making to the hidden states. Basically, C sub t becomes a matrix, and nt becomes a vector, because this here is a vector here. So you're just adding a vector to a vector, and this is adding a matrix to a matrix, where the matrix is dv by dk, and the vector is just going to be dk. So the output here is what they call is, or what they kind of say is, you have these queries which are extracting the values from the hidden state. So you basically have your hidden state here, which is composed of these vectors. So it's composed of dv vectors of dimension dk. And what you do is you multiply by q, so you do an inner product with q. So basically your q vector is extracting the value information, because each of these becomes a scalar whenever you do an inner product by q. So you multiply by q, and you get this output scalar, and you get the output scalar for each part of dv. So the output is going to be dv, and they basically say this is the query is extracting the values from the hidden state, giving you your hidden state here. So inner product giving you dv. The normalization, since this is a vector, you have to do an inner product with the queries. So this gives you a scalar, and this is your normalization. So your normalization is just with your queries. It feels like a weird reference, but to transformers still, but they make the comparison. So key value cache, query is extracting your information from your key value cache, being sent to the next hidden state, and the output via your via this normalization here. You can kind of think of this as, if I have here QKTV, like you basically have, you can reformulate this if you turn softmax into a kernel, and you can do the product between KT and V, and you have your queries extracting the information. So this is just basically the accumulation of Q, KT, and V, and that gives you your output. And that's what we have here. So KV cache, Q is extracting your information, and that gets sent to the next hidden state. So that's all you're changing here. I also drew that out up here. So the additions you're making are mostly in the input state. So your hidden state is similar, except X is being turned into, well, you still have your forget gate. So you have your forget gate and your forget gate here. So you still have your forget gate, and your forget gate is doing its normal forgetting stuff. So that happens here. The main stuff happens in the input when you have your keys and values. So you convert this to keys and values, or queries keys and values. The keys and values, you take an outer product. You then throw this to the input gate, and you add this to CT. So you add this to your context, and you also add this to your normalization state, but just the key. You only add the key to the normalization state. You then throw this through your norm, which is composed of the context and the normalization state. But you also need to add your queries into this norm state. So your norm state is composed of the normalization state, the context state, and your queries. And then you get your output, which is then sent to the next hidden state, and the output. So yeah, basically you're just taking a sLSTM, converting it to a matrix by doing an outer product rather than doing an inner product. That's basically all you're doing. So rather than doing inner product with the weight matrix, you're doing an outer product with two vectors. And then they make the comparison to normal attention. Now, because you're doing this outer product, you don't have this mixing that occurs up here, this memory mixing. So you can basically have multiple heads in parallel. They draw a diagram up here. So if this is your hidden state, HT1 and HT2, in the next hidden state, this becomes your hidden state here. The memory mixes. So HT1 from from one LSTM goes to the hidden state of all other LSTMs because of that mixing. But in here, if you have multiple heads in attention, you know the heads are parallel and they don't mix with each other. So it allows for more efficient computation. So yeah, this meets the things they were trying to do here. One is to revise stored decisions, which they do with the exponential weighing, the limited storage capacity, which they do by making it a matrix, and the lack of parallelism by removing this mixing of information. So now if we look at the results, they look pretty good. But yeah, so here is test of xLSTM. So they call this thing xLSTM. And xLSTM is a mix of sLSTMs and mLSTMs. So they have this matrix, or they have this, not matrix, they have this notation here with brackets where this is basically a mix. So if you add up the values, that's basically, or it's a proportion. So 0 to 1, the first one is saying how much of a mLSTM do you have and how many sLSTM layers do you have. So 0, 1 is saying you have no mLSTM layers and you have one sLSTM layer for every layer. This is saying you have one mLSTM layer and 0 sLSTM layers, and this is saying for every mLSTM layer you have one sLSTM layer. If we go down to here, they do stuff like we have 7 mLSTM layers versus one sLSTM layer. So you have this proportionality here, which they use to examine their model. Overall, it looks pretty good at these different tasks. These are various tasks so that they say they involve like state tracking and stuff like that. If you're curious to look more into the tasks, go ahead. But in general, it looks pretty good overall. The more important tasks are like the language modeling tasks, the one we all really care about. I don't think they do this on images at all, but the language modeling task is kind of the more important task, the one that's used the most. And for this slim pajama task, or for the slim pajama benchmark, which I haven't heard of much, so it's kind of strange that they do it on slim pajama rather than normal benchmarks, but on this task they look at, it beats Llama and GPT-3. It has more parameters than like GPT-3, so that may be why, but it seems to beat it. Now, that's not to say that an xLSTM is better than a GPT model. It probably is not, but on the task that they look at, Slim Pajama, it is at least comparable. So it's not to say that this is a better model than a transformer, it's just comparable. With the other models, with the other linear models, it seems to perform quite well, with RWKV being the best. It's interesting that 4 is better than 5 and 6 for RWKV, but yeah, they compare it with other models and it does pretty good for the Slim Pajama task. It scales. So one problem with an LSTM is it does not scale. So if you increase the number of parameters, it does scale. It doesn't just like die suddenly, which is what you would probably see with an LSTM. For memory capacity, it does quite well for like this recall task. So if we look at the accuracy, xLSTM, so this would be a mLSTM, and this would be an mLSTM and sLSTM. It does quite well overall. It's near Llama for most of these tasks. So as you increase the model dim, the expressive power becomes better, and it can hold more information, being better at recall, as you would expect. So it does quite well on that task. Here, they do some ablation studies, and one interesting thing I saw whenever I looked at this is LSTM layers even needed? I think you can just have an mLSTM. Like I don't think you need any MS LSTM layers because they do this mixing. But here, if you just have mLSTM layers, it's better than if you have a mix between mLSTM and sLSTM layers. And here, they do ablation studies, but if you look at the if you look in the appendix, the model with just mLSTM layers is actually better than the mix with sLSTM and mLSTM layers. So I think you could just need mLSTM layers in this model. I don't think you need any sLSTM layers. Just a side note that I saw whenever reading this paper. During inference, you would expect this thing to do quite well in terms of memory, and it also does quite well in terms of perplexity. So if we look at the perplexity, the models for xLSTM stay pretty low. The perplexity stays low, while for like a llama model, it dies, and that's because of this. That's because of the terrible positional encodings. Adding positional encodings to a transformer gives it terrible extrapolation abilities, while for an LSTM, you don't have any positional encodings, so that allows it to do inference for much longer. The only thing kind of that may give it a problem is maybe the values blow up, but the normalization value should fix that. So xLSTM does much better than the other models. They show a bunch of other tasks showing that xLSTM is much better than the other models, if you're curious to look at it. But this is like every other paper that we've seen. This is obviously the state of the art paper. Probably isn't the state of the art. It probably isn't going to beat Transformers. It's probably going to be somewhat comparable to Transformers. There's probably going to be tasks where it's better. There's probably going to be tasks where it's worse. It's just like RDBKV. It's just like every other linear transformer we've seen. There's tasks where it performs about the same as a transformer. There's tasks where it performs worse than a transformer. This is probably going to be the same as that. So I don't expect this thing to be beating transformers everywhere. Expect this thing to be a replacement or something that could perhaps replace it. We will see once people start implementing this, and once it's tried on like real benchmarks and actually tried, does it actually do like they say? Because sometimes it doesn't even do that. So we'll see. Hopefully this is a good model that does scale and does what they say. We'll find out.